Hello, for Data Communications and Network 1 class today, Ajahn Sana will talk about how to encode the cyclic codes by using chip register circuit. Cyclic code. Okay. The chip register circuit is the hardware that we use to implement the encoder of circuit codes. Okay. And this hardware will compute the parity check sequence based on this equation. The parity check sequence B, vector B, is the remainder of 2 to the n minus k multiplied by vector u divided by vector g. Okay. Since the parity check sequence has n minus k bit, okay, so the chip register has to contain n minus k bit also. For example, if you have nk code, okay, is a 7-fold code. Okay, so n minus k equal to 7 minus 4 equal to 3 bits. Okay, so you must have chip register of 3 bits. Okay, one register will contain 1 bit. Okay, so we have 3 blocks of registers here. Basically, it is a flip-flop. Okay, it's from the digital logic design, it can be like D flip-flop or JK flip-flop. Okay, and okay, so we have these 3 flip-flops here in the chip register circuit, and the structure of the circuit is based on generator polynomials, or the generator sequence is the same, right? Because generator sequence is the coefficient of generator polynomials. Okay, so if we have gx equal to 1 plus x cubed, okay, how do we draw the structure of the circuit? Okay, we can do it like this. Okay, the input, okay, will be data will coming on the right. Okay, and this is we start from the left hand side is the lowest degree. Okay, so gx is 1 plus x cubed, right? So this is x to the 0, so we have this line here, and then we have x, so we have this line here, and then we don't have x squared, so we don't have the feedback. Okay, in the next box here, and then we have x cubed. Okay, be careful that the arrow of x cubed will go up. Okay, then this is the feedback, right? And the shift, okay, may come from left to right. Okay, so we have left to right. If we have 2 arrows, okay, coming down and coming from the left, we must have the modulo 2 arithmetic here, which is an XOR gate. Okay, it's the same as an XOR gate. This one is mod 2, okay, or XOR mod 2 addition, or XOR gate. Okay, and then this one we have 2 arrow, okay, one coming from below and one from the left, so we have the XOR gate, or the modulo 2 over here also. So this is the structure, the same as what I type here, what I draw here. Okay, now if we change the chip register, circuit structure, okay, which means that we change the gx polynomial, okay, of the generator polynomial, then the structure of the code is different. Okay, so it's become a different code. For example, if I use gx instead of 1 plus x squared plus x cubed, I use 1 plus x squared plus x cubed, for example. So I will have, look like this, 1, okay, x, we don't have x, right? We have x squared, we have x cubed, okay, and then we have u coming up from below, so I will have it like this. This is arrow here. Okay, now again, be careful of the arrow direction. We can have in this class, since it's a very short topic, okay, so I show you only one structure of how to implement the chip register circuit with the data coming from the right hand side. If you look at other textbook, okay, maybe there are data coming in from different different side, and but the arrow may not be the same. Okay, if you want to know more about this, okay, we have another class called applied coding, which I will open next semester. Okay, so anyway, for the datacom class, we will teach you only this structure with data in from the right hand side. Okay, data in from the right hand side and the arrow this way. Okay, if we have a different GX, for example, a standard CRC, we have, for example, GX equal to x to the 16 plus x 15 plus x squared plus 1. Okay, we must have n minus k blocks, okay, in the chip resistor circuit, right? And what is n minus k? N minus k is basically the degree of GX. So this, in this case, n minus k equal to 16, right? Because it's the degree of GX, so I have to have 16 blocks, which I will draw like this. Okay, actually we have to draw like all of them, okay, but to make it simple. So anyway, this is x to the 0, and you don't have x to the 1, right? You have x squared here, and then you have x to the 6, x to the 15, and x to the 16. Okay, so we have input here, so we draw it like this. This one we must have the modulo 2 here. Okay, this one we have modulo 2 here like this, and then we have the feedback line here. Okay, so this is the structure of x to the 16 plus x to the 15 plus x squared plus 1. Okay, now let's look at how to encode. Okay, given that we have the chip register circuit already, so I draw it again, draw it many times, okay, to make it, so that you can see it clearly, okay, how to draw this. Okay, so this is the GX of x squared of x cubed plus x plus 1, and we want to find parity polynomial and the copolynomial. When you encode, you want to find the parity polynomial, and as I showed you from last example, okay, the copolynomial is just 2 to x to the n minus k ux plus bx. Okay, so if you get bx, then you get the copolynomial. Okay, so you initial, okay, with all zeros. Okay, in the memory you need to initial with all zero. U is x cubed plus x squared plus x, so u is 1 1 1 0. Okay, with most significant bit on the left. Okay, always, okay, you will input most significant bit first, okay, on the left. Okay, you input first, input MSB first. Okay, this is important. Okay, so we have we input 1 here, so you get 1, and your output from this is 0, right? So 1 plus 0 is 1. Okay, your feedback here 1 and 1. So you get, after the first chip, you get 1 1, and then this one is 0. Okay, so this is after the first chip of most significant bit. Okay, then you have 3 bits left. Okay, after you input the next bit, so it's 1 here, and the shift out is still 0. So 1 plus 0 is 1. So it go down as 1 here. But right now, the output from the first box is 1, right? So 1 plus 1 plus 1, okay, is 0 here. So it becomes 0 here. Okay, then this just shift. Okay, so this is the result of this bit coming in. Then you have 2 bits left. This bit coming in, so you get 1, and this is become 1, right? 1 plus 1 is 0. So 0 going down, 0 and 0 here. So this bit is 0. 0 plus 1 coming out. 1 plus 0 is 1. So this is 1. So this is 0. Okay. So the last bit, okay, last bit coming in. 0 plus 0 is 0. So 0 go down. 0 plus this is 0. Okay, 0 plus 0 is 0. So 0 here and 1 is shift here. So after the last bit coming in, you get the result of 0, 0, 1. This is bx or b, okay, in binary form. So it's x is the coefficient of x to the 0, x to the 1, x squared. So bx equal to x squared, or b equal to 1, 0, 0. We write it like this because we usually put most bit on the left, okay? So this is the polynomial, the parity check polynomial bx, and the parity check sequence b, okay? So what is v? Vx would be, so you multiply this one, okay, with x to the n minus 1, which is x cubed. So you have x to the 6th plus x to the 5th plus x to the 4th, and then you plus bx, okay? And what is bx? Bx is x squared. So this is your code word, okay, which is the same as the last example. And v equal to u, right? Shift to the left, so 1, 1, 1, 0, and then you have vector b is 1, 0, 0, okay? So this is b, and this is the 2 to the n minus k times u, okay? So this is your code word, okay? So you finish the encoding of the of this example of the cyclic code, okay? And this is the I draw it, okay, so that you can maybe read it easily, more easily. But this is the same as what I just wrote down in the last slide. So I summarize this is what I tell you before, that if we shift the data in from the right, okay, then you will shift until the last bit, okay, it's in the leftmost position, and then the next shift will give you bx, okay? It's the same as what I show you in the video, okay? So after the last bit of data come in, that shift will give you the parity check polynomials, okay? The shift of the last bit of data will give you the copolynomial, and you add the post-polynomial to the x to the n minus k ux, and you get the copolynomial, okay? And be careful of the feedback values, okay? If it is a 1, it will change the values of the incoming bit, okay? Let me show you this. Okay, when you want to draw a line here, when you have the XOR gate here, if the feedback here is 1, the value will change 0 to 1, 1 to 0. This means that the feedback is 1. But if the feedback is 0, then the value will not change, okay? So 1 to 1, 0 to 0, this one, the feedback here is 0, okay? So you have to be careful at the line here, because when you cross the boundary which you have in modulo 2 addition or the XOR gate here, it can change the value. But if you don't have the line like this one, you don't have the feedback, okay, no feedback, then you don't have no line, then it's always the same value when you shift, okay? So please be careful on this. And all three methods, okay, must give the same bx, so you can practice by yourself, okay? You use the different data, okay, and you encode it with the model 2 arithmetic, and then you try it with the chip register circuit, and it must give you the same answer if you do it correctly, okay? Now the standard cyclic redundancy check CRC code. The cyclic code is general name that we used, okay, in the field cyclic codes, okay, but in the standard, okay, there are other names. For example, cyclic redundancy check or CRC. So in the standard, you say something like CRC 16. This means that we have 16-bit parity check sequence. We also have CRC 12, okay, CRC 32, okay, CRC 16. And it will be given to you, okay, what is the generator polynomial. So this is the generator polynomial of CRC 16, okay, which is the one that I use as the first example, the example before, okay. So you can search, okay, what is CRC 32, okay, in the website in Google, okay. So this is the end of the of this slide, okay. For next slide, we will talk about decoding methods. Thank you.